My name is Anuj Pradhan. I am an assistant research scientist in the University of Michigan Transportation Research Institute, and I'm here to talk a little bit about my research that has been funded by the Atlas Center. Um, the Atlas Center has funded our research on teen drivers. We want to understand the effect of passenger presence on teen drivers, specifically teen passenger presence on teen drivers, and we want to do that using a driving simulator and a brain imaging technology uh, called FNIRS, or functional near infrared spectroscopy. We received a pilot grant from the Atlas Center to conduct this research last year. We are in the process of collecting data, and we hope that it goes well in terms of the results. Um, in terms of what spurred the interest in this research, I've been doing young driver behavior research for quite a while now, using a driving simulator experimental paradigm to look at driver behavior, young driver behavior. And we've been successful in the past using eye tracking technologies to understand a lot of the behaviors. And we found that the outcome measures from eye tracking uh, told us a lot more about what the driver's doing, what the driver's thinking, um, especially when compared to using outcome measures from the vehicle itself, such as speed or position in the lane and so on. So that's given us quite a bit of information. It's a very useful outcome measure for us to use. But in the meanwhile, there has been quite a bit of advance in brain imaging technologies, and FNIRS, which is functional near infrared spectroscopy, is one such technology that has become quite accessible now. Essentially, what this does is it measures hemodynamic flow in the brain. That basically means the flow of blood in the brain, and looks at oxygenation or deoxygenation of that blood in areas of the brain. And it does this by shining light into the skull and measuring the amount of reflected light. So, in a nutshell, it's a cheaper, simpler, easier way to measure some sort of cortical activity, brain activity, as compared to much more sophisticated technology such as fMRI. The reason we went with FNIRS was that we wanted to be able to measure blood activation in an ecologically valid situation, which means we want to be able to look at brain activation when you are driving, for example. And we have been using driving simulation for a while because it's worked very well in recreating a good platform to measure real driver behavior, and using FNIRS and driving simulation in conjunction was just the next logical step for us to take. So what we're doing right now is we're measuring brain activity of drivers when they're operating a driving simulator. This is a continuation of research that we are conducting already, looking at teen passengers' influences on teen drivers. There is evidence out there in the literature, epidemiological evidence as well as experimental evidence, showing that the influence of teen passengers on teen drivers is significant. There is some evidence from experimental studies that show that teen drivers are prone to taking more risks if there is a teen passenger or if there are multiple teen passengers in the car. We want to understand this phenomenon better. Is it just because of distraction because of the teen teen passenger in the car? Is it because of some form of peer influence because of the teen passengers in the car, or are there other mechanisms in play? We've been looking at eye tracking and driving simulation data to study this, but us looking at brain activation data is pretty novel, and I think definitely an innovative approach to understanding this issue. For the future, like I mentioned, we are collecting data right now for this study, and we hope to find something that will give us a clue as to issues regarding impulse control and response inhibition. Issues are surrounding executive control in teenagers. We do know that there is evidence that the teenage male's brain is still developing, especially in the prefrontal cortex, and there's some evidence that this continues on up till the age of 25 or so. So what are these developmental differences that occur between teenagers and adults in the context of driving is something that we want to understand, especially for executive functioning measures. The future steps for this would be obviously to try and take this pilot data and leverage it into a much bigger and more rigorous study looking at brain activation for drivers. One potential direction it could go in is looking at drivers in a much more realistic environment that is outside the simulator. So for example, maybe in a controlled test track or maybe out in the real road. There are issues associated with this, of course, in terms of safety as well as in terms of technology and measurement and instrumentation. But once we have good pilot data from our ongoing study, we'd be able to learn a lot to inform a larger, more comprehensive study. Impact of this research. That's difficult to measure, but really what we always strive for is safety. Traffic safety, driver safety. Our goal is to reduce the burden of injury, fatal injuries, non-fatal injuries, and we know that young drivers, teen drivers, are overrepresented in crashes in this country. We know that male young drivers are overrepresented. We know that young drivers with peer passengers are even more prone to be in a fatal or a non-fatal crash. And us understanding the mechanisms of what happens in the teenager's brain, in a very simplistic manner, would potentially help us develop programs of intervention, will help us inform education, licensing, learning, and potentially inform policy regarding passenger presence, for example, for teen drivers. And hopefully with some good data, some rich data that we can collect from this pilot and from subsequent studies, we'd be able to establish a good evidence base for teen drivers' brain activity, which will then inform safety-related issues regarding teen behavior.